So this is Engineering Statistics and Linear Algebra 18 EC 44. We are in the module 4. We were doing the 4 fundamental subspaces. So today we'll take more examples of the 4 fundamental subspaces. Going forward, right? Before going forward, we will just try to recall what we have done in the last class. We tried to define what is known as a subspace, and subspace can be a set of vectors that span a space. For example, the column span, for the column span, the column space is one which is considered. Okay, so what you call this description might include the useless vectors, which are the dependent columns. Also, we see that the it can be subspace can be represented by a condition the vectors must satisfy. So in this case, we know that the null space consists of those vectors that satisfy Ax is equal to 0, and this might include the repeated conditions of dependent rows. Okay, so we discussed here the left inverse B and the right inverse C for each of the cases of R equal to M and R equal to M. When R is equal to M, then we will have a two-sided A inverse. So depending upon whether R is equal to N or R is equal to M, we will have the left inverse or the right inverse. Okay, or if we have M equal to N, then we will have the two-sided A inverse. Okay. 4 column spaces are column space, null space, row space, and left null space. Column space and null space we have studied in more detail, where the rank of the column space is R and the null space is N minus R. Row space is nothing but the column space of the transpose of A, and left null space is the null space of the transpose of A. Right? So once we can find this, we can as well find this also, right? So the null space NA and the row space CAT are subspace of R to the power N, and the left null space NAT and the column space of CA are subspace of R to the power M. So that gives us the number of rows and the number of columns here, the order of the number of rows and the number of columns over here. So we have taken an example also in the last class about if we have a simple matrix like this, then column space will be 1, 0, because that will correspond to independent column. Rather, we should try to multiply a C with this 1, 0. Okay, we multiply C with 1, 0. Multiples of this 1, 0 will be the one which corresponds to this. Okay, so the column is the line through 1, 0. That means it is column space can be represented as C into 1, 0. Similarly, row space is the line through 1, 0, 0. The transpose, again, this should be in the column format, and again you can multiply it by a constant to get the row space itself. And that is in R cube because we have 3 elements over here. This is in R squared because this is having 2 elements over here. Similarly, the null space is in R cube because null space will be so to say what you call the space corresponding to this, and the left null space is a line in R squared. So left null space means you take the transpose of the null space, right? And then naturally, if you try to get the what you call left null space corresponding to that will be within the R squared, because then the rows and columns have got interchanged. Then we can try to find the null space also. The null space will have each time we can when we have this, you have only one pivot, and you have 2 free what you call variables, and for each of the free variables you set each of the one free variable to 1 and all other free variables to 0 and find the solution. Then again this you keep on repeating. So that means if you have, in this case you have 3 what you call columns, out of which first column will correspond to the pivot variable, second and third column corresponds to the free variable. So first you set the free variable associated with this as 1 and the other as 0, and do the vice versa. So when you do the first free variable equal to 1 and the other free variable to equal to 0, then you might get this. And if you reverse that, then you'll get this. So similarly, say in case you have 4 free variables, then say x1, x2, x3, x4 are 4 free variables. That's the assumption which I'm making. Really speaking, might be that you'll have x1, x2 as the pivot variables, x3, x4, x5 might be the free variables. So when x3, x4, x5 are the free variables, then first we make x3 equal to 1 and x4 and x5 equal to 0, and then try to solve it. We'll get a equation. You will get a line, okay, like this. And then further make the x4 equal to 1 and x3 and x5 equal to 0, and find the values of the what you call all the x1, x2 also. Similarly, next one, x5 equal to 1 you make, and x3, x4 equal to 0, and find x1, x2. Okay, so like that you can try to find all the values of x1, x2, x3, x4, x5 for each of the cases of one free variable being made 1 and all the other free variables made 0. So in this case, because we have 2 free variables, we'll have 2 columns. Okay, so the what you call, so to say, in this case, the null space will refer to C1 into this plus C2 into this, C1 into this plus C2 into this. Okay, similarly, the left null space will be take the transpose of this and try to find, and that will have only single vector. So all the 4 vectors are column vector. This is very much important. All the 4 vectors are column vectors. Now coming to in detail about the 4 subspaces. Okay, we know null space and column space. So we can discuss the null space and column space and then go for the other 2. So let us see what a null space here is first, and then might be column space, and then we can come back to the row space, and then we can go for the left null space. Okay, so we know the column space of A. Column space of A, to find the column space of A, we need to do the reduction. That is basically the Gauss elimination method. After using the Gauss elimination method, we need to find which are the pivot columns and which are the free columns. Once you find the pivot columns and free columns, then using the pivot columns, the linear combination of the pivot columns in the original A matrix, not the U or R matrix. Okay, pivot are the so to say free variables can be found only after finding U or R. But once we find which is the pivot and which is the free column, then we again need to go back to the A matrix, and whichever correspondingly corresponds to the pivot column, then we take the linear combination of those pivot columns to get the column space. So pivot columns of A are the basis of its column space. Pivot columns of A are the basis of its column space. So that means whatever pivot columns are there in A, you take the linear combination of that to find the column space. Okay, whatever are the pivot columns of A, you take the linear combination of them to find the column space. So dimension of the column space CA equals the rank R. That just means that you can have, if you have 2 pivot columns, then the rank of that will be 2. We know very well. And therefore, the dimension of the column space is R, which is same thing as the number of pivot columns in A, which also equals the dimension of the row space. This also equals the dimension of the row space. That is because now even if we transpose the matrix, definitely the number of rows, column rank and row rank is not going to change. Sorry, forget about transpose. Even when we are given a matrix, then whether we talk about the row rank or the column rank, it will always be same. Okay, rank is just the same. Okay, so which also equals the dimension of the row space. So the number of independent columns equals the number of independent rows. Okay, number of independent columns equals the number of independent rows, which will just give you correspondingly again the number of pivot columns equal to number of pivot rows. So pivot itself is the independent. Wherever we talk about pivot, that itself is independent, and that forms the basis. Okay, so independent or pivot might be interchangeable sometimes. So a basis for CA is formed by the R columns of A that correspond in U to the columns containing the pivots. This is very much important. That's what we have been discussing till now. A basis for CA, to find CA, basis for CA means to find CA. CA is found by using R columns. R columns is the rank is being R, and that will be equal to the number of independent or pivot columns of A that corresponds in U to the columns containing pivot. Column containing pivot means independent columns again. So row rank is equal to column rank. If the rows of the square matrix are linearly independent, then so are the columns and vice versa. Okay. If the rows of the square matrix are linearly independent, then so are the columns. And if columns are independent, then correspondingly the row of the square matrix will be linearly independent. Okay, that's about the column space. And we have seen columns, null space. Null space can be found by solving Ax equal to 0. By solving Ax equal to 0. So the null space of A is same as the null space of U and R. Column space of A is not same as column space of U and R, because we need to go back to A to find the column space. Okay, from U and R, we just find the independent or the pivot columns, and dependent or the free columns. Okay, then depending upon which are the pivot columns, corresponding columns of A are the ones which should be taken to find the column space, whereas the null space of A is same as the null space of U and R, because we are here talking about Ax equal to 0. Ax equal to 0 or Ux equal to 0 or Rx equal to 0, if you try to solve, you'll get the null space. So a null space Na has dimensions n minus r. Null space has dimensions n minus r. Okay, so null space is totally dependent upon how many free or dependent columns are there. How many free or dependent columns are there, and dependent columns will be naturally n minus the independent columns. Okay, independent columns is dimension, rank. Okay, so the special solution are the basis where each free variable is given a value 1. We know that to find the null space, each free variable is given a value 1, while all other free variables are made equal to 0. Okay, we make one of the free variable equal to 1 and all other free variables equal to 0, and try to find the special solution in each case. Okay, so then next time again we go for the next free variable 1 and all other free variables equal to 0, and find another special solution, and this should be repeated. Okay, so then Ax equal to 0 or Ux equal to 0 or Rx equal to 0, it gives the same, gives the pivot variables by back substitution. Okay, so we will get the what you call once we set this one of the free variables to 1 and the other free variables to 0, we can try to find the values of the other pivot variables, and using that you can find the null space. So the null space is also called the kernel of A, and its dimension is n minus r. Okay, that we already mentioned over here. And this dimension n minus r is known as nullity. We also use the term that the dimension of the null space is known as nullity. Dimension of null space is known as nullity. Okay, then we come to the row space of A. So for every U or R, the non-zero rows are the basis, and the row space are the has dimension R. And how do we find row space? Row space of A is the column space of A transpose. So we had connectivity issues. So let us continue from where we have stopped, right? So we are discussing the row space of A, right? So there we said that for every U or R, so whenever we talk about row space of A, it is nothing but the column space of A transpose. So for every U or R, the non-zero rows are a basis and the row space has dimension R. Okay, so the row space A has the same dimension R as the row space of U, and it has the same basis. Again, row space of R also has the same basis because the row space of A, U, and R are the same. Row space of A, U, and R are the same, and that is nothing but the column space of A transpose. So by the method will follow will be same thing as the column space only, but only that you take the A transpose and then try to find the column space of that will be the row space. So now I think we will come to the left null space. Left null space is nothing but the null space of A transpose. Similar to the row space is the column space of the A transpose. We have left null space as the null space of A transpose. So for any matrix, the matrix of pivot variables plus the number of free variables. We know that we can have only pivot variables and free variables in the matrix. Some of them, okay, the number of pivot variables plus the number of free variables must match the total number of columns. Number of pivot variables plus number of free variables must match the total number of columns, and this gives us what is known as rank plus nullity, or rather rank nullity theorem. Rank plus nullity equals n, and that is known as rank nullity theorem or dimensionality theorem. So what does the rank nullity or dimensionality theorem say? It just says that dimension of CA plus dimension of NA is equal to number of columns. Dimension of CA plus dimension of NA is equal to number of columns. Dimension of CA is rank, dimension of NA is nullity. Okay, dimension of CA is rank, dimension of NA is nullity. Sum of those two will give us the number of columns itself. So the left null space n of A transpose has dimensions m minus r. Okay, so you take the transpose of what you call A and then find the null space. It becomes the left null space of A. That's all. Okay, and left null space has dimension which is m minus r. Okay, m minus r. Now this is how we represent the four different spaces. Okay, four different spaces, right? So column space is being mentioned over here. See this here, right hand side, top. Right hand side top is column space, which is referring to all AX. Okay, all AX, right? So this will give you the column space of all AX, and the dimension of that is R, and that is written by the R of A. R of A column space is represented by the what you call CA or RA, whatever you want, right? And the what you call we write over here the dimensionality to be equal to R, right? So then we come over here, what you call this is the column space, and then we'll come to this now, null space. Null space is in the bottom left corner. Null space is in the bottom left corner. Ax equal to 0. This is solution for to find null space. We use Ax equal to 0. To find null space, we use Ax equal to 0. So NA will be the null space which we mentioned, and that has the dimensionality n minus r. Okay, then the what you call from the column space, you can using the method of column space, you can find the row space. Okay, so here we write Ax, and this is you find the column space of A transpose to find the row space. To find the row space, we need to find the column space of A transpose, and the dimensionality of this is R. Okay, dimensionality of this and this both are same, and this is written as R of A transpose, and this will be subset of the Rn. This will be in the space of Rn. This will be in the space of Rm. Okay, dimensionality of this is R. Then coming to the left null space, which is in the bottom right corner, and this is found by finding the null space of A transpose. That is A transpose Y equal to 0 is what we need to solve, or you can say null space of A transpose. That is what is written over here. That is the left null space. It has a dimension which is M minus R. So this is a standard notation for representing the 4 fundamental subspaces of A. 4 fundamental subspaces of A. Okay. Sometimes, you might use U also, but here in particular, we should talk about the 4 fundamental subspaces of A. So again, we are writing it in a little different way. C of A is column space of A with dimension R. N of A is null space of A with dimension N minus R. C of A transpose, this is not A into T, this is A transpose, equal to row space of A, and that is the dimension R. Null space of A transpose is equal to left null space of A, that is the dimension of M minus R. Now let us take this example of another example of this. A is equal to 1, 3, 2, 6, where M equal to N equal to 2. So we are having M equal to N equal to 2, and rank here, if you find the determinant of this matrix A, then you'll get a 0. 1 into 6 minus 2 into 3. 1 into 6 minus 2 into 3 will give you the value equal to 0. That is the determinant. Okay, determinant of this matrix is equal to 0 because 1 into 6 minus 2 into 3 is equal to 0. So because of that, the rank cannot be 2. But if you take the subset of this A, it can be this 1 or this 2 or this 6 or this 3, each one having its own determinants as again 1, 2, 3, 6, whatever. Okay, so that will give us a non-zero determinant, and hence rank is equal to 1. Okay, rank is equal to 1. The way to find rank is first take the what you call determinant of this matrix itself. If doesn't give 0, then that this this is a 2 by 2 matrix, and therefore 2 itself will be the rank. If determinant of this is 0, you need to find take the subset of rather sub matrix of this, and to each of the submatrix you try to find its determinant. If one of them is non-zero, then rank will be now n minus 1 or 2 minus 1, that is equal to 1. Okay. Now the way to find the column space will be, you need to solve this now. You find the Gauss elimination. Try to do the Gauss elimination. How do you do Gauss elimination for this? How do you do Gauss elimination for this? We need to make this 0. Okay, we need to make this 0. What is the way in which we can make it 0? R2 minus 2, 3 R1. R2 minus 3 R1 will make this 0. R2 minus 3 R1 will go into R2. So 3 minus 3 into 1 will be 0, will come here. 6 minus 3 into 2 will again give me 0 over here. So the reduction will give me 1, 2, and 0, 0. So that gives me that this is the pivot or independent column, and this is the dependent column. This gives me the independent column, and this gives me the dependent column. So independent column means we have pivot variable here. Dependent column means we have a free variable here. Okay, because these are 0, 0. If you should see the principal diagonal over here, in the principal diagonal, this is 1, therefore this corresponds to pivot, and this is 0, therefore it corresponds to free. So the column space will be now multiples of 1, 3, multiples of the independent variable, column. Independent column is 1, 3, multiples of 1, 3, multiples of 1, 3, right? Multiples of 1. The second column is in the same direction and contributes nothing new. Okay. Second column, if you multiply each one of this by 2, you will get this. So this is dependent upon this. This is a multiple of this. This is a multiple of this. If you multiply this column by 2, you'll get this. So therefore, there is no information within this. Okay, this doesn't contribute any information. This is sufficient. So therefore, column space is multiple of 1 by 3. Then null space. How do you find null space? We need to write AX equal to 0 and try to solve it. AX equal to 0, A is as it is. Because it is 2 by 2, the value of X should be 2 into 1. Okay, otherwise we can't multiply the two matrices A and X. If I write AX equal to 0, then that just means A you write as it is, X you write it as a column vector which is x1, x2, and 0 vector will be 0, 0 on the right hand side. Now you solve it. If you solve it, what will you get? 1 into x1 plus 2 into x2 is equal to 0. 1 into x1 plus 2 into x2 is equal to 0. So now we have, the x1 as the pivot variable, x2 as the, free variable. We know it very well because we have already reduced 1, 2, 3, 6 by Gauss elimination method. 1, 2, 3, 6 by Gauss elimination method to 1, 0 and 2, 0 over here. 1, 0 here and 2, 0 over here if you apply Gauss elimination method. So therefore, this is the free variable, and this corresponds to the what you call pivot variable. Okay, 2x1 plus 1x1 plus 2x2 equal to 0 is what we'll get. Okay, even you can take the second row also. 3x1 plus 6x2 is equal to 0. Both are same. So either way, if I take here x1 plus 2x2 is equal to 0, now I have only one free variable. If I make that equal to 1, if I make the free variable equal to 1, free variable is 2. So if I make it equal to 1, I'll get x1 plus 2 into 1 is equal to 0. x1 plus 2 into 1 equal to 0. And that will give me, if I take the plus 2 on the other side, I'll get x1 equal to minus 2. So what do I have? x2 equal to 0 and x1 equal to minus 2. Right? x2 equal to 1 and x1 equal to minus 2. If I take x2 equal to 1, this corresponds to the free variable. I'll get the pivot variable over here as x1 plus 2 into 1 equal to 0. That is, x1 is equal to x1 plus 2 equal to 0. That is, x1 equal to minus 2. Okay, so therefore I'll get here minus 2. So that's I can find the null space. So how we have found this? By using ax equal to 0, right? Row space, what do? You just take the what you call transpose of this and find the column space. Same process, whatever we apply. If you take the transpose of this, we'll get 1, 2, 3, 6. 1, 2, 3, 6. So now if you do the reduction, 1, 2 will be the independent column. 3, 6 will be the dependent column for A transpose. For A transpose, 1, 2 will be the independent column, and 3, 6 will be the dependent column, and the row space will be now the multiple of the independent column 1, 2. Independent column 1. Okay, multiples of the independent column 1, 2. Okay, so we write this as the column vector, since strictly speaking it is in the column space of A transpose. Okay. Left null space, how do you find? You take the transpose of this and try to find the null space of that. Okay, so that is A transpose y equal to 0. We try to write A transpose y equal to 0, or you can write A transpose x equal to 0, does not matter at all. Whether you write A transpose x equal to 0 or A transpose y equal to 0, it does not matter at all. Okay, if I write A transpose y equal to 0, I'll get, you can write A transpose, which is, transpose of this matrix. Write the transpose of this matrix. Then multiplied by a vector y, and y or x. How does y look like? y1, y2 in the column space, in the column. y1, y2, only two elements. Okay, because again this is a 2 by 2 matrix. A transpose is also 2 by 2. You can't multiply A transpose with y if the number of elements in y are more than 2 in the columns. Then try to solve for y1, y2. Okay, so again y1 is independent variable and corresponding to independent variable, that is pivot, corresponding to independent column we have pivot variable, corresponding to dependent column we have the free variable. Okay, so again we'll get there the equation 1 y1 plus 3 y2 equal to 0. 1 y1 plus 3 y2 equal to 0. Now y2 is our free variable. If you make it equal to 1, we'll get y1 equal to minus 3. So y2, if you make equal to 1, y1 will be minus 3. So whether you write it as y or x, it hardly matters. Now this will be minus 3, 1. The rows of A with coefficients minus 3 and 1. So multiples of y equal to minus 3 of 1 will be the left null space. Now we need to plot this. Now what did we do? What did we get? Column space is multiple of 1 and 3. Column space is multiple of 1 and 3. So we are plotting this over here like this. Okay, multiples of 1 and 3. So first let us plot 1 and 3, right? 1 and 3. So 1 and 3 will be x value, first this x axis value will be 1, y axis value will be 3. Okay, you can consider this as x1 and this as x2, that doesn't matter. Okay, the x axis value will be 1, y axis value will be 3, right? So y axis value is 3. So we'll get this point. We'll get this point. If you multiply this by 2, you'll get 2 and 6. If you multiply this by 3, you'll get 3 and 9. So that the line joining all those points will be this line. The line joining all those points will be this line. Okay, if you multiply by 0, you'll get 0, 0. So please remember that multiples of 1, 3 will go through 0, 0. Okay, so you join this with 0, 0, we will get the line which corresponds to multiples of 1, 3. Okay, then let us see what is the other one. Then we have the null space which contains multiples of minus 2 and 1. Okay, null space of minus 2 and 1. So this will be corresponding to x's and this corresponds to y's, and therefore that is written like that, right? So null space here will be equal to the value which is multiples of multiples of 2 and minus 1. Multiples of minus 2 and 1, minus 2 and 1. Null space of minus 2 and 1. So null space of this is written a little wrongly, right? Minus 2 and 1. This should not be 2 and minus 1. It should be minus 2 and 1. So minus 2 is this. Okay, minus this is plus 2 and minus 1. Okay, it doesn't matter. Minus 2 and 1 are 2 and minus 1 because you are just trying to multiply by minus. So if you try to write that over here, might be minus 2 and 1. If you try to write, you'll get over here. Okay, you join that by 0, you'll get all those points, right? You'll get all those points. So whether it is 2 and minus 1 or minus 2 and 1, it hardly matters because you are just multiplying it by a constant which is minus 1. Okay, multiplying by a constant which is 1. If you multiply this by a constant, multiple means c into this. If c is minus 1, then this becomes 2 and minus 1. So it hardly matters. Okay, so we will get this point, and you need to join with if you multiply this by 0, 0, you will get this point 0, 0. So all these lines, whether it is this line, this line, this line, this line, all are going through 0, 0. Then we come to the next one, which is the row space containing all